Hello and welcome back, everybody. We are finally on a chapter where we can truly start talking about differential equations, the entire point of this course. But we're going to see throughout the rest of the course that everything we've covered so far is very important. It's very important that we've covered everything we have. Obviously, if your prerequisites coming into the class were strong enough, we could have potentially started here. But I definitely think everything we've covered so far is very, very good that we did. So the chapter is called Functional and Differential Equations. And the first section, we're really just going to start talking about equations in general and kind of move our way up to functional equations and then specify what makes any given functional equation differential. So let's just start here in section 1. This is numerical equations. And I asked the question, this is a little bit philosophical in nature, what is a mathematical equation? And I do have the answer here for you in definition form. That's that an equation is any equality containing at least one unknown variable. Okay, so if you have an equality, you have to state that two things need to be equal to each other, and something inside of the equation needs to remain unknown. We can't necessarily know the answer to any given equation right away as it's stated. And because of this, an equation by itself has no truth value. Okay, because there's an unknown, since we have our variable in the equation, which is undefined, we can't say whether or not any given equation is true or false. But if we then ask ourselves the question, what does it mean to solve an equation? Right? If I said something like x squared plus 2x plus 1 equals 0, that is neither a true or false statement. That's just a statement. But to solve an equation is for me to add an extra idea or an extra definition. If I provide an explicit or implicit definition into my equation, then and that definition makes the equation true, then I've solved the equation. So a solution to any given equation is a definition. Right, so solution to an equation is a definition of the variable. And that definition in particular makes the statement of the equation a true statement. So let's take a quick example here at the bottom. I say, here's an abstract example. And let's consider the superimposition represented by a plus sign of colors of light. I start with the equation where I say green plus an unknown color is cyan. And that statement by itself, if I just consider this as a statement, green plus an unknown color is cyan, is that true or false? Nobody's going to be able to tell me because they don't know what the unknown color is. It's simply a statement. The solution then takes the form, and I should probably add definitional equality here. The solution takes the form, the unknown color has been defined to be blue. And the moment that I make the definition, unknown color is defined to be blue, all of a sudden the equation, green plus unknown color equals cyan, becomes a true statement because I reinterpret unknown color as blue. And now once I give myself unknown color is blue, this statement becomes reinterpreted as green plus blue equals cyan, which everybody can agree is a true statement. So that's kind of the more abstract version of a statement, but let's make our way back into mathematics where we can actually have an equation relating numbers. So here's my equation relating numbers, x squared minus 7 equals 2x. Right now it has no true or false values. I'm just saying x is somewhere in R. No true or false values, and yet I could potentially make a definition for x which allows this statement to be true. That would be finding the solution to the equation. My next example could perhaps be a definition, but I'm leaving it as an example, and I'm going to describe why I call it like this. So I'm saying this is a general numerical equation. So any equation which relates numbers can be written in one variable. Okay, so as long as I restrict myself to one unknown, every equation which relates numbers can be written as g of x equals 0. Okay, g of x being a function defined by the collection of operations on x. So I have some collection of operations I want to perform on my unknown variable x, and I'm going to set that equal to 0. I can write every numerical equation in this manner. Let's just look at it really quickly up here. Is there a way I could rewrite this equation to be g of x equals 0? And I think a lot of you already can tell what this will be. If I shift everything to the left-hand side, I recover x squared minus 7 minus 2x equals 0. If I simply define the left-hand side, definitional is in the wrong direction there. I define the left-hand side to be g of x, then I recover g of x equals 0 represents my equation. Okay, so that's what I mean, and it shouldn't take you very long to convince yourself that yes, this is true. No matter what numerical equation I write down, I can pull everything to the left-hand side and recover gx equals 0. Okay, now we're going to jump into some new notation that you might not have seen unless you've taken Intro to Proofs or something similar. And that's this notation of g inverse, except I'm not putting 0 in here. That's not what I'm writing down. It's not g inverse of 0. G inverse of 0 may or may not exist. But to avoid this whole idea, because inverse functions need to still satisfy the criterion of functions, so rather than placing a number inside of the symbols which represent inverses, what we do is we still use the same symbols as inverses, g to the negative 1. So it's the inverse, but rather than placing a number in there, this 0 is inside of brackets, and the brackets make this the set which contains 0 as the only entry. And I know if you haven't taken the Intro to Proofs course or maybe some other courses in first order logic or set theory, you're going to wonder what the difference is between the set which contains one element and that element itself. It's a very subtle difference and you don't have to worry too much about it. But what I'm trying to emphasize here is that if I'm taking, when you take the notation of a function inverse on a set input is not the same as the function inverse on an input itself. With a set input, it's considered as this word called the preimage. In the preimage, here, the preimage of g on 0 is defined as the set of x's in R, or whatever number system I'm using, such that g of x equals 0. Okay, so you're going to say, what's the difference between that and the inverse function? The difference is that this set could either be empty, right? If there are no x's, for which this is true, the empty set is a perfectly well-defined set. The set might contain only one element, in which case we could have replaced the preimage with the inverse function if it only contains one element, or the set might contain more than one element. If the set contains like 30 different elements, then it's ambiguous what g inverse of 0 would be without the brackets on it. Because g inverse of 0 is trying to say I'm looking for a single number, which is true. And if this set contains 30 numbers, it's really ambiguous what g inverse of 0 means. So that's why we use this special notation with the curly brackets to define the set which contains 0, and then we consider the preimage of the set. That's just to say if we have multiple solutions or no solutions, that this idea is still well defined, that kind of the inverse image is well defined of the element 0. Okay, so then that is how we might be able to find solutions to equations, because if all of our equations are written as g of x equals 0, then in fact for any x in the set, which is the preimage of 0, that x will be a solution to the equation. Okay? So we'll scroll down to the example. The example says find the function g for which the preimage of 0 corresponds to the solution set of the equation. So here's my equation, and I'm looking for a g so that the preimage of 0 satisfies this equation. All I need to do is find g, which by doing that I'm just going to rearrange everything to the left-hand side of my equation, and I'm going to define everything on the left-hand side as g. So when I rearrange everything to the left, I get x squared minus cos 2x. I define the left-hand side as g, x squared minus cos 2x, and then that reduces my equation precisely to g of x equals 0, which means that for that specific preimage, the preimage of 0, for this specific function g, I have found the solution set for my equation. Okay, so that's all we have for section 1, which is nice. Now we're going to move on to section 2, where I basically step up in kind of abstraction away from numbers and into functions. So I'm basically trying to say that there's nothing special. So we have our number numerical equation up here, right? X squared minus 7 is 2x. There's nothing special about me deciding that the x lived in some space of numbers R. I could perfectly well define the exact same equation as f squared minus 7 equals 2f. So basically what I've done is I've replaced every x here with the function f. Okay, So now this is an equation which relates functions to one another, and I don't know still if there is a function which satisfies this equation to make it true. But notice now I'm not searching for x's over the space R, I'm searching for functions which map R to R. So that's the space I'm searching over for maybe a solution to my equation. Now, when it comes to functional equations, I can't stress the next line enough. This is going to be the most important thing we encounter for the rest of differential equations and any other sort of functional equations that you ever encounter in life is the following. This functional equation is specifically interpreted as that the functional equation is satisfied, that the function is equation satisfied numerically when evaluated must be satisfied numerically when evaluated at every x in the domain of the function. I can't get away with solving a function equation if the equation is solved only for a single x in the domain of the functions. That's not enough to satisfy a functional equation. I need this to be true for every single input into my function, that their output squared minus 7 equals 2 times f. So that's how we interpret every functional equation. Every time we see a functional equation, we interpret it as this needs to be a true statement for every input to the function. Okay, so then the question becomes, what is the difference between solving, the non-functional equation, x squared minus 7 equals 2x, versus the functional equation, which contains f's in them? Isn't the complexity there equivalent? And the answer is yes, but it's also kind of no. And we'll see why right now, if I clear this. The first equation has two solutions. Okay, I can use my quadratic formula, right? If I shift my 2x to the left-hand side, all of a sudden x squared minus 2x minus 7, I use the quadratic formula, and that I get 1 plus or minus 2 root 2. Fine. I have two solutions when it comes to the numerical equation. Okay, I'm interpreting the equation numerically, I have two solutions. If I change my view to functions which satisfy this for every input, I can define a function which takes the positive numerical input, or numerical solution to the equation, for an entire range of x's less than x naught. I can choose the negative one for an entire range of x's greater than x naught. And this is a perfectly well-defined function on R. And yet there are infinitely many functions which do this because I have infinitely many choices of x naught in R at which I could split my function up. So a numerical equation may only have finitely many solutions, and then its immediate successor in the functional equation world has infinitely many solutions. And we really do care a lot in mathematics whether or not we have one solution, two solutions, 11 solutions, 14 solutions, or infinitely many. We care about all possible solutions to any given equation for very relevant reasons. If I was trying to predict the future, ideally I can reduce the number of predictions I make as small as possible, so uniqueness is great, and even a low number of solutions to the future is still pretty good for prediction. Infinitely many is not very good. Okay, so here's the true definition of a functional equation. So a functional equation is an equation where the left-hand and right-hand sides take the quote-unquote value of a function, and that's interpreted as the function has a domain and range, that no matter what value I plug into the domain, the value I get out of the range actually satisfies the equation. Okay, so we're able to use the same sorts of equations that we encountered before. So for every numerical equation, we recall every numerical equation could have been written as g of x equals 0. I can also consider its analogous functional equation, g of f equals 0. But I can start to actually broaden my criteria of the g's, which I can create functional equations out of. Okay. If I jump over here, I have an expanded range of operations. For example, I can compose functions. I can take derivatives of functions. I can take antiderivatives of functions. And there are actually a lot of other things I can do as operations on functions that numerically, derivatives didn't make sense in numerical equations. Integrals didn't make sense in numerical equations. Function composition didn't make sense in numerical equations. You can read the above example if you want to. It's just the same thing we were encountering earlier. But I'm going to move on to this next example because here's a nice case where all of a sudden I'm broadening. This is a perfectly valid equation of functions, but it's not a valid equation of numbers because there's no such thing as integrating a number. There's no such thing as taking the derivative of a number. So all of a sudden this equation, I have my function f and I'm able to take a derivative there, two derivatives there, square it, multiply by 2, set it equal to cosine of 2 times a function plus an antiderivative of my function, right? And so we've broadened now this little function g, which now takes functions as inputs. G has a much broader family of operations which we're allowed to put inside of it. We're allowed to put derivatives inside of G. We're allowed to put cosine and function composition inside of G and antiderivatives. And so if we try to do the same thing as we did before, which is basically trying to move this equation to a form where we can say g of f equals 0, I'm going to do the same thing I did before. I'm going to move everything to the left-hand side. Upon moving everything to the left-hand side, I define g. I define the map g. It's a function on functions, g. So I can define that map, which takes in a function and outputs a new function based on the left-hand side. So defining g as the left-hand side there, it's a perfectly valid function on functions to say, okay, I'm going to take in some function, I'm going to take its derivative, subtract 2 times its second derivative squared, minus cosine of 2 times the function, minus the antiderivative of the function. That's a perfectly valid map from functions to other functions. And that map being equal to 0, now we're going to, right, it says right here, with 0 now considered as the constant function equal to 0. The constant function equal to 0 is a function. If I try to evaluate this function on the left-hand side, I want it to be equal to the constant function equal to 0 on the right-hand side. And by defining g, I can still find the pre-image of this 0 being considered as the constant function 0. I can find that pre-image, and that would be a solution to this equation right here. So the solution to either of these top two functional equations is the pre-image of the constant function equal to 0 under this slightly abstract definition of g, where it takes in a function and it outputs a new function based off of these specific operations. Okay, so now I'm going to define a glossary because these are kind of the terms I'm going to use in this course. So that we don't get confused about me saying functions of functions like I have here. Like g is a function, f is a function, but f takes numerical inputs and g takes functional inputs. So I'm going to define some things for this course. We want to keep in mind that these definitions are incorrect in some sense, or what I should say, dangerously ambiguous with respect to math as a whole, because functions can have such a broad meaning and interpretation to them. But let's look at this glossary. I start with just what I'm going to call functions in this course, and that's going to be that my functions are actually functions of number systems, as in their domains are numbers. So I'm going to take any function of c, r, n, or z, and it's just going to be a map from a subset of that number system to itself. And the subset of the number system on which any given function is defined is known as its domain. I think we've all heard this before in pre-calculus even. I'm going to define my function space over some given domain. These are just like our vector spaces. It's the vector space over the field C of functions over some specific domain, right? So as long as all of the functions in my space satisfy, they contain the same domain, and I'm allowed to scale multiply them by complex numbers, then I'm going to call that my function space. Then I'm going to define an operator, and I know you've all heard this term before, but you've probably not known exactly what it means. I'm going to define an operator, and that's going to really be my functions of functions. Okay, so the operator is going to be something which computes over a function space. And that's going to be the well-defined map from some subset maybe of a function space to itself. And the subset of the function space over which any operator is defined is known as its domain. So I'm going to write on the side here what I'm really trying to say is I will use the word function to mean only functions of numbers, and I will use the term operator to mean functions of functions. Okay, if I'm taking one function in and outputting another function, I'm going to call that an operator. But if I put a number in and output another number, I'm going to call that a function. We just have to be aware that in many other courses, we can use the term function to describe a lot of other things that won't necessarily have this form. Okay, so under these definitions, we can now construct what was akin to my general numerical equation earlier, except instead of G, I'm going to use capital letters. Okay, so every time I encounter an operator now, I'm going to use a capital letter. So I'm swapping out my g's from earlier for t's, the operator that I consider, and we'll write our generic functional equation as tf equals 0. So now t is some operator which takes in a function and outputs a new function, and I'm saying that that new function should be the constant function 0. And then to solve this equation, I'm going to search for elements in the preimage of this operator, the preimage of the constant function 0 with respect to this operator. Okay, so I want to just comment quickly on this last line, and I say, this is a story of inversion. Differential equations as a whole is a story of inversion. It's a story of finding the preimage of 0 of some really crazy operators. And they start out easy, they're not that crazy, and they get harder and harder really quickly. So the question is, how hard can it be to reverse the behavior of a function or operator? Turns out it's very hard indeed. So we're going to be spending the rest of the semester trying to figure out how to invert operators as best we can. And in particular, the operators we will be inverting are those which give us differential equations. So let's talk really quickly about differential equations. This is just going to be really an introduction to maybe the vocabulary we're using on differential equations. So this first thing says differential equations are a proper subset of functional equations. Okay, so there are a lot of functional equations that exist that are not differential equations. We are considering a very proper subset here. It's the same way all squares are rectangles, but not all rectangles are squares. Think about differential equations as the square inside of the space of rectangles. So a differential equation is a functional equation, and recall this is how I can write any functional equation, where specifically the operator t contains at least one differential operator. So if I can find a derivative inside of this representation t, if I can find a derivative in there, then all of a sudden I've gained a differential equation. If t doesn't have any derivatives, I no longer have a differential equation. I have some sort of other functional equation. So let's look at some examples. I'm going to call this one the first order linear ODE. So looking at this one, I have a functional equation here. Y prime, I've taken a derivative of y, equals m of t, so I'm going to call that a function of t, times the function y, plus b as a function of t. Okay, so in this case, the unknown y itself is considered as a function of t. And so that's unknown, and suppose that m and b have been prescribed for me. Okay, so m and b I already know, but the y's I do not. So this isn't similar to like my y equals mx plus b formula. We'll find out that's why it's called linear. And in particular, this is a differential equation because I have at least one derivative sitting around. But let's see how we can maybe write it in this form, tf equals 0, to guarantee that it's a differential equation, maybe in a better light. Let's notice now, if I define t on the function f, if I define it to be d dt minus mt on the function f minus b of t, I'm going to define that to be t of f, then my equation actually reduces to t of y equals 0. If I take this operator t that I've defined right here and I act it on y instead of f, and I set that equal to 0, we would find we have the same thing. Let's just do that right now really quick. T of y, by its definition on the left here, is d dt minus m of t on y minus b of t. If I set that equal to 0, and I compute my derivative, I get y prime minus mt y minus bt equals 0. And if I rearrange this equation, that's y prime is mt y plus b of t. And so we see that we recover our original equation under this definition of t. Okay, I'm now presenting a second order constant coefficients ODE. And in particular, we're just calling this second order because we have two derivatives. We're not going to worry too much about it. I'm just trying to describe that this particular functional equation, which contains two derivatives on y, one derivative on y, 0 on y, for some unknown y function of x, and prescribed constants a, b, and c, as well as a function of x and g, is a differential equation by the same idea, where if I now define the operator t to operate on functions f as a times two derivatives plus b times one derivative plus c times 0 derivatives, all on f minus some prescribed function g, then that's actually going to give me the same equation that I started with, so long as I set t of y equal to 0. Right, so t of y equal to 0 under this definition of t gives me exactly my differential equation. Here I have something I call the separable ODE. You can read through that one yourself. Believe me, you can write it in terms of a differential operator. Here I have what's called the wave equation, which deals with partial derivatives instead of regular derivatives, or ordinary derivatives as we would call it in ordinary differential equations. These are partial differential equations, and you can verify that that is also a differential equation because the operator t as defined, which agrees with that equation, would contain differential operators in it. Okay. Okay, so now I'm actually going to include a definition which will become important for your homework, and this is the definition of an ordinary differential equation. The definition of an ordinary differential equation is any differential equation which in particular can be written in the form of the following, where I have one big function f which takes in my independent variable of time in this case, as well as a lot of derivatives of x. Okay, x is now my function that I'm searching in this case, so x equals xt, perhaps vector valued function of time. As long as I can write the equation in this form for some other function f, then I have what's called an ordinary differential equation. ODE means only one independent variable. That's just something to remember here. One independent variable is ODE. Not one dimension, right? We can exist in higher dimensions, but we only have one independent variable, one input to all of our functions. Now the ordinary differential equations which don't depend on time, up here I have f, which depends on time t. Down here I look at this one and f does not depend on time t, right? So I've dropped the dependence of my function on time explicitly, right? Because each of the x's themselves are functions of time, but this function f, which kind of defines my ODE, does not depend on time. So autonomous means the function which defines the ODE does not explicitly depend on time. That's what autonomous means. It means it's when you think about any autonomous process, that process kind of exists all by itself. So it exists independent of time, except for our derivatives there. Okay, now these two definitions are going to be a little bit broader than we actually want all of our definitions to look like for ODEs. We're going to be a little bit more specific on the ODEs that we're going to study in this course, and those are actually going to be the ODEs that look like the following. X prime equals f of t and x. Okay, so I have the first derivative of perhaps a vector valued x, vector valued function of time, and that equals f, a function of time, as well as the vector that we're looking for as our solution to the ODE. Now, this is a little bit strange as to why all of a sudden from n derivatives on x, we've reduced ourselves to one derivative on x, but that's going to be the subject of the next section in the book. So for now, just trust me that all of the ODEs we're going to study in this course can take this form. We won't always put them in this form, but they can take this form. So this is something, if you have to remember what does an ODE that you might know how to solve look like, it looks like this. The ODEs you and I care about can be represented like this. Now, just to check that we're paying attention, what would the autonomous version of this ODE be? It would be that f does not depend on time. So once again, autonomous means it doesn't depend on time. Okay. And then very quickly, I know this is a bit of an aside and the video is going fairly long. Very quickly, I'm going to discuss what's called a multi-index notation for differential operators. And this is just to introduce you to PDEs. We're not going to be tackling PDEs in this course, but it's nice for you to at least see what they look like in general. So multi-index notation is simply that given a collection of variables, remember in PDEs, I can have multiple independent variables. So here these x's are my independent variables, and some vector with the same length as those variables. I'm only going to let the values of the vector take positive integer values. I suppose I include 0 as well. We define the operator capital D to the alpha is each of the partial derivatives of my independent variables, and then taken to the power of the elements of the vector alpha. Okay, so that's just like a notation you can look at if you want to. We're not going to quiz on this. We're not going to test on this. We're not going to have homework on this. This is just for partial differential equations if you ever need reference. Moreover, the magnitude of that vector is called the order of the multi-index. So talking about PDEs very briefly, a PDE is any differential equation which can be written as f of. Now this x is actually now our independent variables, and then we're taking a collection of partial differential, right? We're taking a collection of partial differential operators on the unknown function u in this case. So some function of the independent variables and all sorts of partial derivatives on u equals 0. That's going to be a PDE. Okay, so here's the little remark. You might be overwhelmed by that notation, and that's why that's not what this course is for. This is really an introduction to ODEs courses. Once we feel really comfortable with ODEs, we can graduate to PDEs. But PDEs are just a crazy area of active research because they can get really, really insane really quickly. All right, so sorry it's been long.